Hi, I'm Jerome, and today we'll be going through the CJC Prelim exams for H2 Physics Paper 1. First question. The table below shows the estimate of some physical quantities, and we are asked which row is not a reasonable estimate. So the first one is whether the current used in an electric kettle can be 8 amps. So one way to find that out is to find the power output of 8 amps. So the power will be equal to I times V, our current times our voltage. We know that our voltage in Singapore is 240 volts and the current is 8 amps, so 8 times 240, that gives us 1920, which is quite a reasonable estimate for an electric kettle, so we'll just cross that out. Next, the mass of an adult male being 70 kg. Well, I know a few people who are 70 kg, so that's a pretty reasonable estimate. B is also out. C, the speed of an Olympic sprint runner being 10 meters per second. So we just have to recall that the world record was done for the 100-meter race was clocked by Usain Bolt in about 9.58 seconds, or let's just round that to 10 for easy measurements, which is 10 meters per second. So C is also a reasonable estimate, meaning that our answer is D, but let's try to find why D is unreasonable. Well, the water pressure at the bottom of a public swimming pool is given by first the atmospheric pressure, and then in addition to the water pressure from the water itself. So the atmospheric pressure is already 10 to the power of 5 pascals, so which is one order of magnitude more than 10 to the power of 4, which is why it's pretty unreasonable. It will be more than 10 to the power of 5 because we haven't even added our water pressure yet. So our answer is D. The water pressure being 10 to the power of 4 pascals is not a reasonable estimate. Question 2. A potential difference is carefully measured with a high quality instrument and found to be 2.321 volts. So that looks like our ground truth. Two students using two different methods to measure the PD quotes the potential difference as 2.33 volts and 2.344 volts. And then we are asked about the accuracy and the precision of the two different readings. So the precision of this reading, the 2.344 one, is 0.001, which is more precise than the reading of the first potential difference 2.33, which is only 0.01 precision. That means that the 2.33 is less precise than the 2.344 reading. So anything saying that it's more precise is wrong. Next, the 2.33 reading is closer to our ground truth actually than our 2.344 one. That means it's more accurate. So our answer here is B. Question 3. A man is parachuting towards the earth. According to Newton's third law of motion, the force which makes an action-reaction pair with the gravitational force on the man is. So we have our man and our earth, and then the force in question is the gravitational force by the earth on the man. So an application of Newton's third law would state that the reaction pair would be the force by the man on the earth due to gravity. So the gravitational force on the earth due to the man. Our answer here is A. Question 4. We have a non-uniform rod XY being balanced horizontally on top of a triangular wedge. That means initially the center of gravity is resting on the wedge itself. So our center of gravity is here, and we can take it as the weight is acting at this point O. So they tell us that O is a distance of 1.10 meters away from X, and then we are later told that a 1.5 kg mass is hung from a distance 0.2 meters away from X, so this being 0.2 meters. And then we are told that the rod now needs to be moved 0.25 meters to the right to balance horizontally. So I'll just move the wedge to the left instead, it's the same thing. And then this is 0.25. And then there's no more this wedge, so this wedge is no longer a thing, but the weight is still acting at O. And then we are asked what the mass of the rod is. So pretty simple here, we just use our moments. We realize that the clockwise moments provided by this 1.5 kg weight is equal to the, or rather the anti-clockwise moment given by this weight is equal to the clockwise moment given by our weight of the rod. Let's call this weight W. And so we just have to equate it. So let's write an equation here, 1.5 kg times G, right, is equal to times the distance from our pivot point, which is 1.10 meters, 1.10 meters minus 0.2 minus 0.25, that is this length, alright, equals to the mass of our rod, let's call it M, times G, the gravitational field strength of the Earth, times 0.25, which is this distance, the perpendicular distance of our center of gravity from our pivot point. So cancelling out G and rearranging the equation, we have M equals to 1.5 times this distance. Putting that into our calculator, that's 1.1 minus 0.2 minus 0.25, giving us 0.65. So 1.5 times 0.65 divided by 0.25, that gives us 3.9 kg. So answer is B. Question 5. A resultant force F acts on a mass of 0.15 kilograms. The variation with time t of F is shown on the diagram below. Let me just convert this to kilograms here. Alright, so we have a force acting in the negative direction in the start, and then after that slowly it becomes positive after 2 seconds. Yep, and we are told at time t the mass is moving with a velocity of 2 meters per second. So when t is equal to 0, the mass is moving with a velocity of 2 meters per second. Let's take this direction to be positive, and we are asked what the speed of the mass is at t equals to 3 seconds after all these forces have been applied. So what we should do is use our impulse momentum theorem, which states that the force times the time over which the force has been applied, or rather the area under the curve here from 0 seconds to 3 seconds, this is equal to our change in momentum of our object. And the area under the curve here is, so this part is negative and this part is positive, and they both cancel out. So an easier way for us to calculate the area is to just take the area of this triangle right here, and this triangle is half times 2 negative 2.0 times 1.0 seconds, and that gives us negative 1 kg meter per second if we want to put it in units. And so that is our change in momentum. But remember that we are looking for the change in velocity, or we are rather looking for the final velocity which needs the change in velocity, and the change in velocity is equal to our change in momentum, 1 kg per meter second per meter, 1 kg meter per second divided by our mass. So that is -1 divided by 0.15, and that gives us -6.7 to 2SF. So our change in velocity, our final velocity, is equal to our initial velocity, which is 2.0 meters per second, plus our change in velocity, which is -6.7, and that gives us -4.7. But we're asked what is the speed of the mass, so we can ignore the minus sign. Our answer here is B. Question 6. The diagram below shows a wooden block in its upright position with these dimensions, and we are given the density of the wood. So using this, we can actually find the mass of the wood, and we are asked what is the submerged depth of the wooden block when it floats upright in water, and we're given the density of the water to help us here. So we have water over here, and we have the block submerged upright, and using Archimedes' principle, our buoyant force is equal to our weight of our block when it's in equilibrium, and Archimedes' principle tells us that our buoyant force is equal to the weight of the water displaced by the submerged part. So that gives us the density of water times the volume of submerged part times G, which is our gravitational field strength. That's for the upward force. And our weight of the block is the density of the block times our volume of the block times our gravitational field strength. We can cancel out G on both sides and then try to solve for this. So our density of the water is 1000 times the volume of our submerged part, which is H. Let's call this depth that we're trying to look for H, times 3.5 times 1.0. That's the volume of the submerged part of the block. That equals to 850, which is our density of the block, times the volume of the block, 1.0 times 3.5 times 7. And because this is MCQ, let's try to cancel as much as we can. Don't do calculations when we don't need to. That gives us H equals to 850 times 7.0 divided by 1000. And if you put that into your calculator, the answer is about 5.95. So our answer is 6. Question 7. A block starts to slide down a 30-degree slope from rest, as shown in the figure below. Assume that the friction on the block is negligible. We are asked what the final speed of the block is after it has traveled 10 meters down the slope. Alright, so let's try to draw a free body diagram to find out what is the resultant force on the block. Here we got our weight of the block, and then here we have our normal reaction force to the block, and our resultant force of the block is here, and this is parallel to the incline of the slope. We realize that because the normal reaction force is perpendicular to our incline of the slope, this is 30 degrees. If we do our trigonometry, that means that this resultant force is mg sine 30. And that also means that our acceleration of the block is equal to g sine 30 degrees, which equals to half g, because sine 30 is half. So we have the acceleration of our block, and we have the displacement of our block, 10 meters. And we have the initial velocity of our block, u, which equals to 0 because it slides down from rest. So to get the final speed, we use this equation, which by the way is also found in the formula sheet. V squared equals to u squared plus 2as. U is 0, 2as is 2.5 cancels out. Let's just take g times 10 meters equals to v squared, and that is actually 9.81 times 10, which is 98.1. That gives us v, our final velocity, as 9.9 meters per second. Our answer is C. Question 8. A body of mass 90 kilograms travels along a horizontal road at a speed of 5 meters per second. It then accelerates at 1.5 meters per second, so it has to output some force to accelerate. At the time it begins to accelerate, the total resistive force acting on the car is 200 newtons. So on top of the force that it takes to accelerate, it must output even more force to overcome the resistive forces. So there's the force that it takes to accelerate, and then there's even more forces to overcome the resistive forces. And then we are asked what the output power is developed by the car as it begins this acceleration. So the speed is 5.0, and then so our strategy here should be to find the total output force of the car times the velocity, which is 5.0, to give the instantaneous power as it begins the acceleration. To find this total power output, we just find the acceleration force, which we have to calculate, plus the resistive force, or the force that the car outputs to overcome the resistive force, which we are given as 200 newtons over here. So that equals to F accelerate plus the resistive force times the velocity, and the acceleration is the mass of the car times the acceleration of the car. That's the force that the car outputs in order to accelerate. So our power output is equal to 90 kilograms times 1.5 meters per second squared plus 200 newtons times 5.0. Putting that into our calculators, that gives us 1700 to 2SF, so our answer is B. Question 9. A car is making a circular turn of radius r with speed v, and we are given that the centripetal force on the car is F. So the radius is r, the speed is v, the centripetal force is F. Let's try to draw this out. It's a circular turn. This is the radius, and then let's say this is the car. It's traveling at a speed v, and the force, the centripetal force, is F. Alright, what is the centripetal force when it makes the same turn at a speed of 2v? So now we have a new velocity, 2v. So remember, and we are asked what is r, and it's the same turn. So this we are asked what is F, it's the same turn, so r is the same. So remember that our centripetal force is just the mass of the car times the velocity squared over r, mv squared over r. M is the same because it's the same car. V in this case becomes 2v, so 2v squared, and r is the same r because it's the same turn. So the new force let's call this the old force, equals to 4mv squared over r, which equals to 4 times the old force. And our answer is D. Question 10. A small sphere is moving in a vertical circle at constant speed. So it's very important here. And then we are asked about the magnitude of the resultant force on the sphere, which we should interpret this as the centripetal force, because the sphere is moving in a circle. Petal force at the bottom of the circle compared to the top. Alright, yeah, all the options concern the resultant force at the bottom as compared to the top. So let's see. This is our circle. At the bottom there's this resultant force. At the top there is also this resultant force, which gives the centripetal force. What we have to remember here is the centripetal force is given by mv squared over r. V is our speed, m is our mass of the object, r is the radius of the circle. Because it's the same circle, r is the same. Because it's the same object, m is the same. And because it's moving at constant speed, v is the same. So take note here that the resultant force does not change. So it's the same at the top of the loop as it is at the bottom of the circle. Our answer here is D. Question 11. We are told that the neutral point in the gravitational field between the Sun, the Earth and the Moon is the point at which the resultant gravitational field due to the three bodies is 0. That doesn't mean that there isn't any gravitational force on the object by the three bodies. It just means that the resultant force from the gravitational forces is 0. And then we're told that the mass of the Earth is about 80 times that the mass of the Moon, and then we're asked which position it's possible for the neutral point to be, and we are given a picture over here with positions A, B, C and D. So what we want to do is first recall that the gravitational field strength is G big M, which is the mass of our body, like the mass of our Sun or the mass of our Earth or the Moon. The gravitational force is Gm, then the mass of our object, over r squared, where r is the distance, let's say our object is here, between the object and the center of the body. So in order for the resultant gravitational field strength to be 0, let me just erase this first. We cannot have it being too strongly attracted to any one of these bodies, in order to just be sucked in. If not, the gravitational field strength from the other bodies cannot overcome. So like for example A is wrong here because it's too close to the Sun, and the Sun has a massive big M here. Oh sorry, yeah, the Sun has a massive big M, and after that if your R is too small, if your R away from the Sun is too small, you'll just be sucked in big time, and the resultant gravitational force will not be 0, so it cannot be A. A is wrong. By the same principle, it cannot be B or C because they are too close to the Earth and will be sucked in. So we have D. D is close to the Moon, but don't worry because this big M, the mass of the Moon, is actually very small relative to the Earth and the Sun, so that's not an issue. So we want our R to actually be smaller for the Moon in order to compensate for that. So our answer is D. Question 12. Which statement about two satellites of different masses in the geostationary orbit around the Earth is incorrect? So important, let's recall what is the geostationary orbit. Basically, is when a satellite orbits at a height whereby the angular velocity of the satellite is the same as the angular velocity of the Earth, or basically the satellite turns the same amount as the Earth, at the same rate as the Earth. So from an observer from Earth, you see that the satellite is turning at the same rate of you. Relative to you, the satellite is being stationary. That's why we call it geostationary. So two satellites in geostationary object in orbit have the same height away from the Earth and the same angular velocities. Now, with that in mind, let's try to look at the options. 1. The gravitational forces acting on the two satellites are different. Now, the gravitational force acting on the two satellites is gm m over r squared. Well, r squared is the same because they are the same height. Because both of them are in geostationary orbit, the m's are different. Big M is the same. Big M is the mass of the Earth, and g is a constant, so g is the same because the masses of the objects themselves are different. The gravitational forces are indeed different. So A is correct, but we're looking for an option that is incorrect. So A is not our answer. B. The centripetal acceleration of each satellite is different. Now let's try to find the we try to recall that the centripetal acceleration. A, let me just write as that as A, that equals to our that equals to omega squared r, where omega is our angular velocity of the object. Now, because the objects are both in geostationary orbit, and as we discussed just now, when an object is in geostationary orbit, the angular velocity is the same as the Earth and the same as each other. So the centripetal, because omega is the same and r is the same, the centripetal acceleration of the satellite cannot be different. So B is incorrect and B is our answer. But just for completeness, let's look at options C and options D. So C, the total energy of each satellite is different. Well, the total energy of each satellite is given by the KE of the satellite plus the gravitational potential energy. Now, without going into too much detail, that if you calculate it out, the KE, this you will get gm big M small m over r times half, and that depends on the mass of the object. So the total energy of each satellite is different. C is not our answer. Now, some of you might be wondering, how did we get this from KE plus GPE? Well, it takes a bit of time to derive, but just a guide, to find the KE we have half mv squared, and to find V we just use omega times r. And for GPE, and then we find omega in terms of the gravitational, we find omega r in terms of the gravitational acceleration, which we can find in terms of gmm and r. So that gives us our KE, and our GP, that gives us a KE of half g big M small m over r, and our GPE is just our mass times the gravitational potential, which equals to the mass times negative big G big M over r, and adding those two up we get this negative half gmm over r, which is why C is wrong. Now, option D, the angular velocity of the two satellites are the same. So the angular velocity of the two satellites are the same because they are both in geostationary orbit, so D is not our answer. Question 13. Two monoatomic gases X and Y are in thermal equilibrium in a mixture. This tells us that they are at the same temperature. And then the molecular mass of gas Y is half the molecular mass of gas X. Then we ask the root mean square speed of the gas. We're told that the root mean square speed of gas Y is V. and we are asked what the RMS speed of the molecules of gas X are. So first, let's use the thermal equilibrium. Because they are in thermal equilibrium, they have the same temperature. Because they have the same temperature, the average Ke of gas X is equal to the average Ke of gas Y, meaning half the masses of the molecules of gas X times V squared, which is the velocity of the average velocity of the molecules of gas X, equals to half times the masses, the molecular mass of gas Y times V, because we are told that the root mean square speed of the molecules of gas Y is V, so we'll just use V here, so it's V squared. And then cancelling out our half and realizing that the molecular mass of gas Y is half that of gas X, so this is just half over here. We have Vx squared equals to V squared over 2, and so our Vx, our root mean square speed of our gas X, equals to V over root 2. So our answer for 13 is B. Question 14. We are told that a piston is pushed very slowly into a metal cylinder containing an ideal gas. Now two things here, push very slowly and metal cylinder. Metal cylinder means that heat can be lost to the surroundings. So, and then we are told if the temperature of the gas does not change in the process, which of these statements is incorrect? So first thing we should note is that the temperature of the gas does not change. That means delta T, our temperature is equal to 0. And because our change in internal energy equals to nR delta T, that means that our change in energy, in internal energy of the gas, is also 0. Now, using our first law of thermodynamics, we have the change in internal energy is equal to the work done on the object plus the heat supplied to the object. Meaning that because this is 0, the work done on the object is equal to the heat loss from the object. And A is correct, but we are looking for something that's incorrect here, so A is not our answer. B, the pressure of the gas increases. Now we use, because this is an ideal gas, we have PV equals to nRT, and because T doesn't change, T is a constant, this whole thing is a constant right here. Meaning, because we push the piston down, the volume decreases, that means the pressure has to increase to make up for it. B is correct, so it's not the answer we're looking for. C, the average kinetic energy of the gas molecules increases due to the work done of the gas, but recall that the average kinetic energy of the gas molecules is dependent on the temperature. So if the temperature does not change, the average Ke of the gas molecules don't change as well. So C is incorrect and is the answer we're looking for. Let's look at D. The internal energy of the gas remains constant as we shown before. Note the change in internal energy is 0, so there is no change in the internal energy. The internal energy remains constant. They are the same thing. D is correct, so D is not our answer. So for 14, our answer is C. Question 15. A small mass undergoes simple harmonic motion about a point O. So let's try to draw this. Say this is point O, then the object goes up, then after that it goes down, it goes up in simple harmonic motion with amplitude x naught and period t. So how about we try to graph this, and then let's say at t equals to 0, the object is at point O. It doesn't really matter, but let's just say. And then, so graphing this, because you have simple harmonic motion, we have a sine wave over here with the amplitude x naught and the period t. And then writing this out, we have x equals to x naught sine 2 pi over t, because that is our angular velocity times t. Right, so this is our equation, and then we are asked, is displacement x from O at a time blah 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 after passing through O is, all we have to do is sub t for 1/6 t. So x at 1/6 t is equal to xo sine 1/6 t. This cancels out, so 2 pi is actually pi over 3. And then that gives us, remember that sine pi over 3 or sine 60 degrees is root 3 over 2 xo. So our answer is D. Question 16, we have a mass m on a smooth horizontal table, meaning no frictional forces, attached by 2 light springs to 2 fixed supports as shown below, and then we are told that it executes SHM of amplitude A and period t. We can model its displacement x as some amplitude times, let's say sine or cosine, it really doesn't matter, times the angular velocity, which is 2 pi over t times t. Alright, and then we are asked what the total energy of oscillation is. What we can do to find the total energy of oscillation is to find its kinetic energy when it's at the midpoint, when it's at the center of oscillation, because at that point all the energy is in the kinetic energy, and the kinetic energy is equals to half mv squared. So all we have to do is to find the max kinetic energy is to find the max velocity, and remember that velocity is the derivative of our position with respect to time. An easy way to visualize this, or an easy way to keep our facts straight, is to just differentiate this. So this is equal to a 2 pi over t times cosine our angular velocity times time. And then our max velocity is when this cosine is equal to 1, meaning when our velocity equals to this. So our max Ke is equals to half mv, which as we shown before is 2 pi a over t squared. And that gives us 2 m pi squared a squared over t squared. 2 pi squared m a squared over t squared. Our answer is D. Question 17. A sound wave of frequency 400 Hz is traveling in air at a speed of 320 meters per second squared. This is our velocity, and we are asked what is the difference in phase of 2 points 0.2 meters apart. And yep, we're asked what the phase difference is. So actually our phase difference is just this 0.2 divided by lambda, and to find lambda we just take v equals to f lambda, or lambda equals to v over f. And actually this thing, let's just organize it first before we put it in. This is equals to 0.2 f over v. So putting that in our calculator, 0.2 times our frequency, which is 400, divided by our speed, which is 320, that gives us 1 over 4. but our phase difference is times 2 pi. So that gives us half pi. Our phase difference is half pi radians, because this 0.2 over lambda is in terms of how many periods, but in terms of radians we have to times 2 pi radians per period. Figure 18, question 18, figure 1 shows how the displacement of a wave varies with distance along the wave at one particular time. Figure 2 shows how the displacement of one particular point P of the same wave varies with time. This is our point P. And this graph shows the displacement of P with time, and we notice that it first moves upwards, meaning that our wave here is actually traveling to the left. That's why our P can move upwards. So with that in mind, we are asked which of the following graphs correctly depicts the displacement time graph for point Q. So first we observe what is the initial displacement of point Q, which is 0.5 x naught going down. We just cancel out anything that doesn't start from 0.5 x naught, which is only B in this case. Next, because the wave is traveling to the left, the next direction that Q will go is downwards, because it will go to like this point but shifted to the left, meaning that anything that doesn't start with 0.5 x naught and goes downwards should be eliminated. A is eliminated, and that leaves us with C and D. Now the difference in C and D is that Q for D, the maximum amplitude for Q is 0.5 x naught, but that is not the case, because when the wave travels left and then when Q goes here, it eventually goes back up to this point. This point is actually x naught, so the maximum point for Q will be x naught, not half x naught. That means D is wrong. That means C is correct. Our answer here is C. Question 19, two identical narrow slits S1 and S2 are illuminated with light of wavelength lambda from a point source P. And then we're told if, as shown in the diagram above, the light is then allowed to fall on the screen, and if m is a positive integer, m being in the options we are given here, 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 and here. The condition for constructive interference at Q is, so the condition for constructive interference is that the path difference must be an integer multiple of lambda, lambda being our wavelength. So the path difference is essentially the difference in length that the two light paths will travel. So one light path will go here along x1 to x3, and then that is x1 plus x3. That is the length of this path, and then the other path that the light will go will be to x2 and x4 minus x2 plus x4, and that is our path difference, and that must be equal to some integer multiple of our wavelength. So scrolling down, D looks the most similar. We just replace n with m, and because m is an integer given in the question, our answer is D. Question 20. A beam of light that consists of all wavelengths between 480 and 600 is projected onto a diffraction grating that contains 500 lines per millimeter, and we are asked what is the maximum number of complete continuous spectra that can be observed emerging from the grating. So that might be a bit confusing. Let's try to draw it out to see how it's like. Let me use a different color for this, because colors will be important later. Using dark gray for our diffraction grating, and let's say this is our light. Alright, and let's say this is our wall. So when the light travels, let's say we have blue light. So blue light has a small frequency, blue light has a high frequency and a small wavelength. And then remember, because d sine theta is equal to our n lambda, where n is the order of diffraction and lambda is our wavelength. The smaller the wavelength, and because d is the spacing between the diffraction gratings, which doesn't change, if lambda decreases, sine theta will have to decrease, meaning theta will have to decrease itself. Meaning, the smaller the wavelength, the smaller the diffraction angle. So let's say we have a blue light that comes here, and then it goes and hits the wall here at some angle theta. And then let's take another color with a longer wavelength. Let's say red. Red has a longer wavelength than blue. So we start off here, red. And then because the wavelength increased, sine theta will also have to increase. That means theta will have to increase. That means this is a bigger angle for the same order refraction. So this is our angle theta. Alright, and here let's see if I can find a yellow. I can't really find a yellow. Let's just take this yellow light somewhere in between, right? And then so theta will be in between the two thetas for yellow, so it will go somewhere in the middle. So what we realize here is that there will be a continuous spectra over here for, let's say, oh, this is ugly. Let's change back our color to black. And let me erase that. Alright, so over here there will be a continuous spectrum on the first order, and similarly there will be a continuous spectrum somewhere that looks like this. And then we have our red. I wouldn't draw yellow anymore. For our second order, oh no, what happened? Alright, so for our second order over here, and we are essentially asked how many complete spectrums can we observe emerging from the grating. So complete means that it has to contain all the colors from 480 nanometers to 600 nanometers. Alright, actually I got that mixed up. From 480 nanometers, which is this point, and 600 nanometers, which is this point. Yeah, actually I didn't get them mixed up. I was correct all along. Next, so in order for our continuous spectrum to contain all the colors from this range, we essentially have to find out what is the maximum order of diffraction that can occur for 600 nanometers with that grating. So take lambda equals to the largest wavelength, because that will produce the largest theta for a certain diffraction order, equals to 600 nanometers, and we rearrange this to have lambda n over d equals to sine theta. And remember that sine theta is less than or equal to 1, which means that our diffraction order n is less than or equal to d over lambda. Alright, so we just have to put this in numbers. Let me just write this on the next line. I'm running out of space. D is 500 lines per millimeter, meaning 1 millimeter, 10 times 10, 1.0 times 10 to the power minus 3 divided by 500 divided by our wavelength. Our wavelength here is 600 nanometers. So 600 times 10 to the power minus 9, and that equals, putting that into my calculator, 1 to the power of minus 3 over 500 times 600 times 10 to the power of minus 9. That is 3.3. So n is less than 3.3. The maximum order that can happen is the third order diffraction. That means for our longest wavelength, which I will represent with red. Oh no. Anyway, so this is the second, this is the first, and then the maximum that can happen is the third, and nothing more than that. So same thing the other side, first, second, third, and nothing more than that. So in total there are only 6 continuous spectra. 6 from 1, 2, 3, 4, 5, 6. So our answer here, switching back to our original color blue, is A. Let me just erase some things to give us a bit of space. Alright, nice. Question 21. We are given the charge of a uranium nucleus and we are asked what is the potential at the midpoint between a uranium nucleus and an alpha particle if they are separated by this distance. So we have our uranium nucleus here, and then we have our alpha particle, which is actually just a helium nucleus. And we have the midpoint here, and we ask what the potential is at that point. And that potential is just the potential at that point from the uranium nucleus plus the potential from the alpha particle actually. And remember that the potential from a point charge is given by Q, which is the charge, divided by 4 pi epsilon naught, which is given in the formula sheet, times r, where r is the distance between our point charge and the point at which we are finding the potential of. So this thing is r over here, same thing here, this thing is also r because it's at the midpoint. So r over here we can just replace with d over 2, where d is this value. Let's call this value d. So the charge of our uranium nucleus plus the charge of our alpha particle which is actually 2e, where e is the charge of a proton, so 2e over 4 pi epsilon naught d over 2, then that equals to 1.5 times 10 to the power of minus 17 coulombs plus the charge of an alpha particle, which is 2e, which if you go to your formula sheet to find the value of e, you'll get 3.2 times 10 to the power of minus 19, that's 2e, divided by 4 pi times epsilon naught, which is 8.85, times 10 to the power of minus 12, times half our distance, which is 0.5 times 10 to the power of minus 13. And if you put that in your calculator, you'll get V equals to 2.8 times 10 to the power of 6 volts. So our answer here is C. Question 22. A velocity selector has an electric field strength of this is our E, produced by two, let's see if I can draw here, produced by 2 horizontal plates. The upper plate is connected to a positive potential and the lower plate is earthed. That means that the direction of electric field is downwards and the electric force on the protons will be downwards. Next, a magnetic field of flux density 1.5 times 10 to the power of minus 2 Teslas directed into the plane of the paper. So this is our B field. Is at right angle to the electric field as shown in the diagram. And if we use Fleming's left-hand rule, we will realize, because if remember that using Fleming's left-hand rule, your thumb is the force, your index finger is the magnetic field, and your middle finger is the current. And because the beam of protons is traveling to the right, just take the current as traveling to the right and your index finger pointing into the plane of the paper. You realize that in fact the magnetic force is upwards. So this is our magnetic force, and downwards is our electric force, or the force from our electric field. So we have two opposing forces right now, and we are asked which could be the possible speed of the proton and the observation, whether it's undeflected or deflected downwards or deflected upwards. Because if the magnetic field is, the force from the magnetic field is stronger than the force from the electric field, then the protons will be deflected upwards and vice versa. Alright, so let's try to find the magnetic field, or the magnetic force is actually, if you recall, given by BQV, where B is the magnetic field strength, which we are given 1.5 times 10 to the power minus 2 Teslas. Q is the charge of our protons, and V is the velocity of our protons. And the electric field, or the electric force, is actually just equal to the strength of our electric field times Q. And if our magnetic force is greater than our electric, then it will deflect upwards, and vice versa. If the magnetic force is less than electric, it will deflect downwards. So let's just write BQV less than QE. We can conveniently cancel out Q on both sides, and then we rearrange this to get E over B. Alright, so right now the critical velocity that is in question here is the electric field strength divided by the magnetic field. And if this is above 1, then or rather if the velocity is greater than E over B, then the protons will be deflected upwards, and if it's less, then the protons will be deflected downwards, and if it's equal, then the protons will be undeflected. So calculating this, we have 3.0 times 10 to the power of 5 over 1.5 times 10 to the power of minus 2. That gives us 2.0 times 10 to the power of 7. So recall, anything greater than this, we will deflect upwards. Anything less than this, we will deflect downwards. Equal to this, we will be undeflected. The A, 1.8 is less than this, it cannot be undeflected. If it's less than this, it should be deflected downwards. B is equal to this, it should be undeflected, but it says deflected downwards, so B is wrong. C is greater than this, it should be deflected upwards, but the option says deflected downwards, so C is wrong as well. D is greater than 2.0 times 10 to the power 7, and it says deflected upwards. That is correct, so our answer here is D. Question 23. When four identical resistors are connected as shown in the diagram 1, the ammeter reads 1.0 amps and the voltmeter reads 0, and then we are asked what are the meter readings in diagram 2. And diagram 2 is slightly different. The position of the batteries and the voltmeters are swapped. So one thing we can do actually is to redraw diagram 2 into something more similar to diagram 1. So what I'll do first is draw out the battery portion. So this is the battery. I'll use the highlighter to indicate portions of the diagram that I already redrew. So we have our battery branch here, And notice that in this diagram too, the battery branch is parallel to this branch over here, containing two resistors and an ammeter. So let's draw that out accordingly. It's parallel to an ammeter and two resistors. The part connected to a voltmeter I'll address later. And next, we realize that our battery is also connected in parallel to this branch containing two resistors. So drawing that out as well, our two resistors connected in parallel with the battery. And then the last part that we haven't redrew yet is this branch containing the voltmeter. So this is connected in between the resistors, drawing that out in our redrawn diagram. And what we realize actually is that this diagram is actually the same as this diagram. So the voltmeter reading and ammeter reading should be the same. Our answer is A. Question 24. The diagram below shows a setup of two current carrying wires X and Y and a singleton coil Z. And we're told that wire X has this length and this current, and wire X has this length and this current, wire Y has this length and this current, and coil Z has this diameter, that means its radius is 0.10, and this current. And then we're asked what is the resultant force on wire X. If the center of coil Z is on wire X, the force on wire X comes from both the magnetic force on wire X from the magnetic field of wire Y and the magnetic force on wire X from the magnetic field on coil Z. So using our right hand curl rule, we find that so it's turning the magnetic field produced by wire Y. So this is wire Y, this is the current, and this is the magnetic field. And X is at this position. So the magnetic field from wire Y or wire X is coming out of the plane of the paper here. Same thing with coil Z. If we use our right hand curl rule, we realize that the magnetic field coming out of coil Z is also coming out of the plane of the paper. So BY and BZ are both in the same direction, and to find the total magnetic field strength at the point at which wire X is at, we just have to take B equals to the magnetic field from wire Y and the magnetic field from wire Z. Now why do we want to find the magnetic field at wire X? Because the force on wire X is given by BIL, where B is the magnetic field over here that we will calculate later, I is the current going through wire X, and L is the length of wire X. So later, once we find this, we'll get our answer, but first we have to find the combined magnetic field strength. So the BY, the magnetic field or the magnetic flux density coming out from wire Y, is given by this equation, mu naught I over 2 pi d. This is found in your formula sheet, by the way. So let's go through these constants one by one. Mu naught is the constant, also found in your formula sheet. I is the current going through wire Y, and 2 pi d. D is the distance of your point at which you're trying to find the magnetic flux of from wire Y. So this is this distance, and that distance is 0.10 because it's the radius of coil Z. So that's BY. Now let's try to find BZ. In your formula sheet, the magnetic flux density of a single coil is given by mu naught N, where N is the number of turns around your coil. In this case is 1. I is the current going through coil Z, over 2R, where R is your radius. And putting in the numbers for that, mu naught is 4 pi times 10 to the power of minus 7. IY is 0.5 amperes. given over here, and then over 2 pi, and then d is 0.10 meters plus mu naught 4 pi times 10 to the power minus 7. N is 1, remember, because it's the number of turns around your coil, and in this case coil Z is a single coil, so times 1 times IZ, the current flowing through Z, that is 1.5 all over 2 times the radius of the coil, 0.10. And let me just erase this BIL, we'll get to it later. So if you calculate that using your calculator, you will get 1.042 times 10 to the power of 5 minus 5, sorry, and that is in Teslas. So now that we got B, to find the force, we just have to get BIL, and then that is 1.042 times 10 to the power of 10. Oh my, let me erase that. Okay, 1.042 times 10 to the power of minus 5 times I, the current flowing through wire X, 1.0 amps times the length of your wire L, so it's 0.050, and that gives us a answer of 5.2 times 10 to the power of minus 7 newtons. So answer here is C. Question 25. Diagram A shows an aluminium rod moving away from point O at right angles to a uniform magnetic field. Diagram B shows the variation of time t of its displacement s from O, so basically how far to the right it has traveled from O. And we are asked which diagram or which graph best shows the variation with t of the EMF induced in the rod. So one thing we have to remember is that by Faraday's law, actually the more general form of Faraday's law is that our induced EMF is equal to the rate of change of magnetic flux linkage with respect to time. But in our case, we have a moving rod. So more specifically, this formula will be more pertinent to our question right here. Epsilon, which is our induced EMF, equals to L, the length of the rod, times V, the velocity of the rod it's moving at, times B. And usually there will be some angle involved, so cosine the angle at which, but because our rod is perpendicular to it, we don't have to worry about that angle. So now that we have that, we know that the induced EMF is actually proportional to the velocity. Well, B doesn't change and L doesn't change because it's the same magnetic field and the same rod we are talking about here. So all we have to do is find that E is proportional to the velocity or the displacement or the derivative of the displacement with respect to time. In other words, the gradient of this graph. So for the first part, we realize that because the first part of the graph is a straight line, the velocity over here should be a constant, non-zero constant. So anything that doesn't have the first part as a non-zero constant, we can immediately cross out. That means B and C. So we are only left with A and D. And let's look at the second part to see what happens. At the second part, we realize that the velocity is decreasing, and we know that because the gradient at this, sorry, that's not a very straight line. Let me try to draw that again. The gradient at this point is, oh my, the gradient at this point is steeper than the gradient at this point, meaning that we are actually having a decrease in the velocity. So D is wrong because at D the velocity doesn't increase, the velocity, or rather the induced EMF doesn't decrease, it increases, but our velocity is decreasing and our induced EMF is proportional to our velocity, so our induced EMF should also be decreasing as shown here in A, option A. So our answer here is A. Question 6, we are given the equation of a sinusoidal current, and we are asked which equation represents another sinusoidal current with the period and amplitude doubled. So in our original equation, this is our amplitude given by I0, the period is inside omega, our angular velocity. Remember that omega is equal to 2 pi over our period, so our period is here. So to get our new equation, we just have to take I with the new amplitude. So since our original amplitude was I0, our new amplitude is 2I0 times sine, and originally our period was t, so or inside omega 2 pi over t. But now that our period has doubled, 2 pi over 2t, this equals to half 2 pi over t, which equals to half omega. So half omega is our new angular velocity, half omega times t. So that is our new equation. Our answer here is D. Question 27. We are given that part of the energy diagram of a certain atom shown below. So we have the energy levels, the level 1, level 2 and level 3, and we're told that the energy spacing between level 1 and 2, so this energy spacing is 3 times that. So 3 times that between 2 and 3, so 3 times that of this spacing. Alright, and then we are told that if an electron makes a transition from level 3 to level 2, then we get some radiation of wavelength lambda. So from level 3 to level 2, if the electron jumps, then the radiation we get, the photon, has a wavelength of lambda. Alright, and then we are asked which possible radiation wavelength might be produced by the other transitions between the 3 energy levels. So let's first identify what other transitions other than 3 to 2 that can be. Let me just erase this so we have space. Other than 3 to 2, remember that we also have 2 to 1. And even more importantly, because some of us we might forget sometimes, we also have the energy jump from 3 to 1. Alright, so the lambdas of the energy jump from 3 to 1 and the jump from 2 to 1. Alright, and the second thing that we have to remember is that the energy of the photon that is emitted when the electron makes the jump in energy levels is equal to the difference in energy levels itself. So remember that the energy level of a photon is equal to hf, or is also equal to hc over lambda, because c equals to f lambda. Alright, so this is the energy level. Because we are using lambda here, this is actually the energy level of the jump between level 3 to level 2. Alright, and remember that because this is 3 times this, let me just erase that. This energy jump between 3 to 1 is 4 times the original energy jump from 3 to 2, and this energy jump from 2 to 1 is equal to 3 times that of 3 to 2. Okay, now that we got that out of the way, the lambda for this, so we have to have some hc over some new lambda to produce the same thing. We realize that a lambda over 3 will give 3 hc over lambda, and that will give us 3, our original our original energy jump from levels 3 to 2. So hc over, or rather lambda over 3, is one of the wavelengths that will be produced by the other transitions. Same thing with 4 here, we can similarly see that hc over lambda over 4 will produce an energy jump of 4 hc over lambda, which equals to this thing. Alright, so lambda over 3 and lambda over 4 are both possible. B is correct. Question 28. Which one of the following statements referring to a photoelectric emission is true? Now, if you're not familiar with the photoelectric effect, reading the options might not be that useful. So here's just a recap. So basically, Einstein, he realized that if I took a piece of metal that contains electrons and I shone a flash of light of a certain frequency, sometimes what he realized was that the electrons will be emitted. So the electrons will basically fly out. And then he basically got really curious and he tried this experiment with different frequencies of light and different intensities of light to basically see when the electrons will be emitted. And what he discovered was pretty fascinating. You might even say Nobel Prize winning. What he discovered was that this is the frequency and this is the energy, or the average, or the kinetic energy of the emitted electrons, right? It's actually the stopping potential, but they are the same thing. So what he discovered that below a threshold frequency, which we will call F0, the electrons basically weren't emitted, no matter how high the intensity you shone the light at the metal was. They just wouldn't be emitted. The Ke of the electrons would be 0. But after that, then the frequency will be linearly related to the kinetic energy of the electrons emitted. So that's the first thing he discovered. The second thing he discovered, testing the intensity, right, was that if you took a frequency below the threshold frequency, no matter how high, how intense the light you shone at the piece of metal was, there wouldn't be any electrons being ejected. But above this threshold frequency, right, let me just cross, this graph doesn't represent the frequency, this graph represents the intensity. He measured the intensity against the rate of emissions of electrons, photo emissions. So for a frequency that was above our threshold frequency, the intensity was basically proportional to our rate of photoelectric emissions. But below that, it was just, if frequency was less than our threshold frequency, it was just basically 0. And then this experiment basically won him his Nobel Prize. But so now that we had a understanding of what the photoelectric experiment is, let's try to answer the questions. So the first option, A, no emissions of electron occurs for very low intensity illumination even if the illumination's frequency is above the threshold frequency. That is not true actually. Remember that over here, if the frequency of light we shown is above the threshold frequency, the rate of photoelectric emission will be directly proportional to the intensity of light shown. So as long as you've shown some light, there would be emission of electrons. So A is wrong. B, for a given metal, there is a minimum frequency of radiation below which no emission occurs. Yep, that is true. That is the pretty shocking thing that he found, is basically what this graph means. So below a certain frequency, there will be no emission occurs regardless of the intensity at which you shone the light on the metal. So B is our answer here, but just for completeness, let's look at C and D. C, the velocity of the emitted electrons is proportional to the intensity of the incident radiation. No, that's not true actually. The velocity of the emitted electrons is linearly related to our frequency. It's dependent on our frequency if our frequency is above the threshold voltage. But all the intensity changes is the rate at which our electrons are emitted, not the kinetic energy of the emitted electrons. So if you've shown a higher intensity, the electrons will be emitted with more electrons will be emitted in a given time, but they will all have the same KE. So C is not true. And D, the number of electrons emitted per second is dependent on the threshold frequency of the given metal. Now the number of electrons emitted per second is basically our rate of photo emission. No, it's not dependent on the frequency of incident photon. It's not dependent on our threshold frequency. It's dependent on our intensity, as long as the frequency is above the threshold frequency. But once it's above, it doesn't matter how high the threshold frequency was, our rate of photo emission is not dependent on it. So our answer here for question 28 is B. Question 29. Which one of the following best represents the number n of alpha particles emitted from a radioactive source possessing energy E? So alpha particles emitted means this is alpha radiation. What we can tell from alpha radiation is that we have a radioactive substance X, and then it decays into its daughter nucleus plus a alpha particle, which is actually helium-42. Let's say this X has original mass number m and proton number p. Y will have m minus 4 and proton number p minus 2. So we have the X nucleus originally, then it splits up into the Y nucleus and the alpha particle, which is helium. And then to conserve energy, because some mass is lost in this process, the daughter nucleus Y will have to travel with some velocity, and to conserve momentum, the helium will also have to travel, the alpha particle will also have to travel in the opposite direction with some kinetic energy. Now, taking conservation of energy gives us one equation, and taking the conservation of momentum gives us another equation. So actually, if you work that out, there is only one fixed energy level for the alpha particle to have. If not, one of these will be broken, either the conservation of energy or conservation of momentum for any other value that you find, which means that there can only be one energy level, meaning that our answer is D. There cannot be any continuous energy levels of the alpha particles shown in the other options here. Question 30. Which nuclide has the greatest initial activity? So we are given the amount in moles of the nuclides and the half-lives. So realize that activity is given by our radioactive constant times the number of, basically the amount of particles in number of radioactive nucleuses there are. And remember that our radioactive constant is given by the half-life, or rather is given by ln 2 divided by our half-life, and times n. And remember that n is given by the number of moles, which I'll put in small n, times Avogadro's constant. That's just the definition of the mole. So ln 2 over t half-life. And realize that this is actually proportional to the number of moles over the half-life. So if this increases, if we have the greatest ratio of the number of moles to the half-life, we will have the greatest activity, initial activity at least. So all we have to do now is calculate the number of moles divided by the half-life for each of these nuclides. For option A, that is 0.7 divided by the half-life, which is 2100. As long as we are all using the same units, we don't really have to worry about it. That is 0.12333 dot dot dot. Alright, this MCQ, we don't really have to care about these standard figure, these significant figures. Option B, the amount of moles is 0.002 divided by the half-life, which is 10. This gives us 0.1232, which is less than A. We are looking for the greatest ratio, so B is wrong. The ratio for C is 0.09 divided by 400, and that gives us 0.000225, still less than A. C is also wrong. And option D, our last option, let's see if it's greater than A. 0.09 divided by 4800. Oh my, it's probably not. Yup, it's 0.0001875, which is way too small. So D is out. Our answer for question 30 is A. If you like this video, hit like and subscribe, and head over to our channel for more videos like this.